This is Peter Felfer from the University of Erlangen again, and today we're going to be continuing what we've been doing in terms of atom probe analysis from last time. So just for everyone that's joining in newly, all of the code that you need you'll find on GitHub. So if you go GitHub atom probe tutorials, you'll find all the code necessary. It's updated always before the tutorials, and sometimes during the tutorials. So just stay updated on GitHub, and I will say if we need anything new. The new things that we have for this time are actually things related to local proxigrams. So making proximity histograms from local areas on iso concentration surfaces and alike. I don't think we're going to have enough time today to go to interfacial axis mapping or local interfacial axis calculations. We'll do that next time, but today we'll probably get to do some local proxigrams and and continue or finish off some of the volumetric stuff we did last time. And also I've put this one in. This will probably help you guys a lot out there as well, which is just a convenience function that allows you to load in atom probe data in Matlab, and it will split up the different the POS file into sub POS variables and ranges and everything that you need to work with. So how many of you still have last week's .raw file that we've generated, which we wanted to visualize in Blender, the volumetric file? Do you still have that one, or should we generate a new one? We should generate a new one, right? By the way, also one thing I remembered from last time, it's something I already used to know, that I didn't remember last time. This is about isosurfaces in Matlab. For some reason, the isosurface program in Matlab has X and Y switched. So when we calculate the isosurfaces, we need to make sure that in the mesh grid that X and Y are swapped. It's rotated 90 degrees. It's stupid, but anyway, it's what it is. I've got no handle over that. So let's get started and do some volumetric data first. Create an isosurface, and then we'll go and mark parts of the isosurface and try to get a proximity histogram from parts of the isosurface. The first thing we do is load in the data. Does everyone still have the data set we used last time? The one we got from Lisa? No, that wasn't on GitHub. We're not going to put that up on GitHub. It's ongoing research. We can't put that up on the web for people. So if not, just I think Jan has it on his laptop, and he can just pass it on. We'll need the POS file and the range file, the RNG file. I think she sent me an RNG as well. I can pass it on to you guys as well if you want to. I haven't written a function to load it into Matlab from the rRNG file, just from the RNG file. Let me just check if we've got sound on YouTube. I think that was an ongoing issue. Okay, is there any sound? Okay, is there any sound? Okay, there is sound. Okay, that's not pretty trippy. It actually keeps doing it because of the delay. Anyway, yep. So, what's your thumb drive called? No, that's the wrong one. So, no. Okay, where did I save the other one? It's R5600211. R R5600211 EPOS. So it must be in that folder. RNG, there we go. But I can't see your thumb drive anywhere. Maybe it's on the back. I'm not gonna look for it there. I'm just gonna email it to all of you. Is that the you all got internet, right? Um, come on, it must be. Hmm. Now it's in. I think it was just not in. Anyway, if you're out there and if you're not part of Erlangen, you will just have to use your own data, just simply because. Bloody hell. No cursing on YouTube. Anyway, I'll start doing it. So while you're copying, you can just watch. It's pretty simple. So what you need to do is go onto wherever that range file was, which I great. So go where that range file was, open the range file, and then the polyatomic. So with the range file, with these complicated data sets, what you have is you have a block of range files that comes first, and then you have a polyatomic extension. The polyatomic extension is just for coloring. So all of the ranges that are not all of the ranges of these polyatomic ranges, for example, the one that goes from 17.9 to 18 point something, you will also find here. Sorry, 7.8, 18.1. You'll also find here. So all you need to do is go from the top left corner here to the end of whatever's here and copy that, and replace the commas with decimal points. So command find, comma, replace with decimal point, replace all, and go and copy that. And I will at some point write a function that does a formatting as well. For now, we'll just use Excel, paste. My Excel has already remembered what it is that I want. And the last thing we have to do with the formatting is to go and move all of the entries up here to the right, so that they match up properly. Because otherwise, it just had empty strings here. Okay, do you all have your range files in Excel? Okay. The reason for that is simply when we copy it into Matlab later, otherwise it will be shifted otherwise. Let's go copy. Go right. RNG equals empty cells, and then paste Excel data. And we need to make sure that these two are empty, otherwise you would have to move everything to the right here. just check. The point of the whole thing is that once you've loaded it in like this, all you need to do is load in your pos file. Pos equals read pos in this case. Improve tutorials. And then go and just run the function. Run the function and splits everything up. Just called read XLS ranges. So you just go read XLS ranges. And then you need your ranges, R and G. Your pos variable, POS. And then you need to tell it either nothing, and then you get all the different ions back, just like you would do, for example, in IVAS. The other option you have is to put in atomic, which is what we're going to use right now, so we don't need to fiddle around with where the atoms are. Fiddle around when we want to calculate the concentration of certain species, because we're going to use aluminium and tungsten for the volume, like last time. So just type in atomic as a string, and that's the whole command. Okay, does everyone have the ranges loaded in? Let me have a look then. Okay, so we made sure that everyone here is on the same page. And once you've got those variables, you just let the program run. It's not a particularly fast one. I've just written it in a way that it's easy to read for people. And then you get all of the variables you need to work on the right side here. So you've got, for every element, you've got a pos file, and for each range you've got a range variable as well. So you can go, for example, in Hafnium ranges, and you'll see Hafnium ranges from here to here, here to here, and so on and so forth. Of course, in this case, we're not going to need the ranges anymore, so I might just go and curb them, which we could potentially do in the program. One thing you might notice is that there is no variable for H2O and OH. And the reason for that is that we decomposed atomically, so it made a variable for all the oxygen and it made a variable for all the hydrogen. So in order for clustering programs to not screw up, one thing I've done is, when it makes multiple copies of the atomic positions in case of multi-atomic ions, what it does is that it shifts each ionic location by a certain offset. So if you go into the program, you can see it says offset increment. So for example, if we've got a C2 variable, it takes all the C2 locations and then adds another copy of that offset by the offset increment, which is in this case 100th of a nanometer or 0.1 angstroms, which, considering the resolution of the atom probe, is actually quite reasonable. If you think it needs to shift it by less, you could make that smaller as well. Always remember, we're working with single precision floating point numbers. That's why I didn't by default make it smaller. Okay, so you might have large set increments, especially. So if you're measuring nanowires and your nanowire data set might be a micron long or 2 microns long even, then you might be running out of trailing digits behind a decimal point. This is why it's not set to 0.0001 or something like that. Anyway, it's just so that it's not numerically at the exact same position, because some of the programs would have a problem with that. Okay, does everyone have the ranges? Okay, I just hear that it seems that some of the Matlab versions seem to have an issue with there being an underscore in a variable name. In this case, just go into the actual program and scroll down where it at some point there will be writing the range variable into the base workspace, and there is a string which adds RNG to the name. Just get rid of the underscore, and then scroll down a little more, and there will be another one towards the end. Just get rid of the underscore. I don't know if there's a difference between Matlab on Windows and Matlab on Mac. I didn't have an issue on Mac, but it seems that there was an issue on the Windows machines. Because well, the question is whether is the ranges and the post files and the post variables. Yeah, I just deleted all the ranges, just because we're not going to be working with the ranges from now on. I should probably make that an option in the read XLS function where it dumps all the ranges into your base workspace as well. But for now, it's just dumping the ranges and the variables. Steffen, everything fine? Good. The volumetrics is actually added. If the volumetrics folder is not added to your damn it. Just add the volumetrics to your path by going right-click, add to path, select these folders and there's no subfolder, but add to path, select these folders and subfolders, because we're going to need to use the volumetrics again to calculate the voxelization. Sowieso nicht ständig, macht das ja nicht. Macht das, wenn man eine neue Analyse anfängt, machen das einmal. Okay, I just explained that the program on your laptop. This is a pretty fast app that I'm using here. It's a current MacBook Pro with a Core i7, so it does things reasonably fast. On your laptop, if it's a little bit of an older laptop, it might actually take a little bit longer. But I wrote it in a way that the program itself is pretty easy to understand, mainly because in this case you don't do it all the time. You load in your data once, and it might take 30 seconds, but if it doesn't influence what's happening later anyway. And then we'll go back to the voxelization. The voxelization. So if you've added the volumetrics path, we'll just go voxelization grid vector equals point to voxel of our pos file, which is, so this is the voxelization of our pos file, and we're voxelizing with the voxel step size of 4 nanometers. which is a little bit large. Maybe I think I've set that a little bit too large. So maybe 3 nanometers. I think on Lisa's data set 3 nanometers might be quite reasonable. And again, we get the voxelization and we get the grid vectors that we're going to use. And what other voxelizations did we use? We used aluminium voxelization. Yep. So this variable from the second iteration on, actually this doesn't do anything anymore. Sorry? Aluminium underscore pos. And tungsten underscore pos. And then we have the concentration. Okay, so this is pretty much how far we gotten with calculating the isosurface last time. And what the area in this case was, then the isosurface was twisted by 90 degrees, which because we didn't go any further, we didn't really notice that. But if we would have started plotting atoms together with the isosurface, we would have started noticing that things don't really fit together. So F equals isosurface. So when you calculate the isosurface, what I said about it being twisted by 90 degrees. So when you calculate the isosurface, you just need to start with grid vector 2, which is y values, grid vector 1, and then grid vector 3, and not 1, 2, 3s, but you need to do 2 through 1, 3. And an ISO value, what did we have as an ISO value last time? I think 8%. I think something like that. 6%, 0.06. And we've got the isosurface. Let me just plot it. Patch FV. That looks like an isosurface of Lisa's data. To the command window. Okay, how far? Sorry, I'll just close that so you can see all the commands. How far are you right now? Okay, which means you're here, right? Okay, Steffen. Okay. for everyone that already has an isosurface, the next thing we're going to do is actually pick a specific isosurface. Because if you want to do, you can keep working with whatever it is. But probably if you're working with isosurface, first of all, you might want to pick a specific isosurface. And the other thing you might want to do is get rid of all that lint out there that's sort of clinging on. This is actually, you can't see it that well from just looking at it, but all of these little things, all these little patches, they're all at the surface of the data set. Maybe it would be good to write some code that actually cleans out the voxels that are happening at the right at the surface or close to the hull. But for now, all of these little bits and pieces, they're all hanging off of the edge of the hull. And for that, I've added a little. It's not actually something I've programmed. I've downloaded it from Matlab. But anyway, I've copied it in. I think it's retaining the original copyright notice, and it's called split FV. So let's just call this variable SP or whatever. Is split FV of FV. Oh, do I need to? Let's try it this way. I think I just called it out last time. Split FV. Oh no, it does it that way as well. So SP equals split FV of that patch, and what you get is a vector of patches with all of everything separated by connectivity. So all of the things that belong together, all of the surface elements that belong together form one patch. So for example, if I then wanna, and of course you can have a look and see how large they are, and most of them are like really small. They're the little bits and pieces at the boundary of the data set, but some are much smaller, much larger. For example, here you've got one with 1,700 faces, and so on and so forth. But as you can imagine, you've got 300 of those, and it's pretty easy to chuck out those that are really small. But we might just want to plot them all, and then just select the ones that we want. So we go number of patches equals length of split, which I put just red, or sorry, so it's 321. So we'll create a new figure. Hold on, so it dumps everything into that figure, and then go for I equals 1 to 321, or let's just call it numpatch. So we might want to recycle that. Patch, and then in the patch command we'll go sp I, and we'll probably want to give it different colors, so we'll randomize the colors, and so we'll just go random number 1 by 3. So each patch will have a different color, and then end, and now it's obviously busy plotting. Shouldn't take too long, hopefully. By the way, generating random colors this way is not actually the best way of doing it, simply because it makes the colors relatively dark. Anyway, we'll get into color theory another day. But well, why that would be. Point is, you can see we've got a lot of different like little bits and pieces dangling off, and we can see which ones actually stuck together. So maybe our ISO value wasn't actually all that great, because if I look at all these precipitates here, you can see they're all connected, and I don't think they should be connected. So each of those, like these two, they shouldn't be connected. This one's by itself, but like all of these blue ones are connected. These two ones are connected, just by this very narrow non-manifold point. Actually, later when we do really high-end analysis, we'll get into what manifolds are and what non-manifold points are and why they are bad and how to get rid of them. And yeah, but anyway, so these two are stuck together as well, which means what I'm gonna do is just change the isosurface to a higher ISO value. So we'll make it 8%, while everyone else is. So we'll split that up. Number of patches is 290, so we've got a few less. And then, yep, oh, sorry, 4. There's a 4 command. 401 to new patch. And, oops, now I've drawn it into the same figure. That was not a good idea. Anyway, I'll just get rid of that one and repeat the whole thing. 4, 1, 2, there, and okay, does everyone have an isosurface? So, well, that's it looks a little bit better. Still not great. A few of those have actually separated. dran? Hast du die Isosurface? So now just to show you, if you wanted to export now one single isosurface, they're all different objects. So you can go in and, for example, choose this one here by taking a picker, and now we've picked that isosurface. You can see the sort of handles around it, and export it for analysis by going patch to obj and not putting in a variable. In this case, it knows that if you've picked something in a figure, that's the obj it's supposed to export. So I'll just call that test precipitate save. Now remember, it was sort of this like this spherical little missing one half little thing. Anyway, it's just for demonstration purposes. You can go. Genau. File, import wavefront. Remember Y forward, Z up, very important. Number of tutorials, test precipitate. Oh, yeah, there we go. And there's our test precipitate, and we've only got that one here. And of course, it's got artifacts coming from it being margin cube's isosurface, but it's a topic for another day. I should maybe also make a little function called pick patch, where you can pick the patch and it will load it out of the figure and create a variable for you. But for now, at least you can export it, and you could load it back in if you want to do analysis. And I think the patch to obj also takes arrays of objs and makes them different objects. But I've forgotten what I've implemented that or not. One thing you can see here is, of course, that all that lint that we're talking about is all happening at the surface because there is voxels with bad statistics. Of course, if you use a smoothing algorithm like the commercial programs, then all of that would be gone. There's a good smoothing algorithm also in that folder. You can just let it run and see if all those little bits and pieces here vanish. But for now, I'd actually prefer we work with the raw algorithm and then later add some other stuff on top, just so you can see what the effects are of different smoothing algorithms. Because there's always, of course, the danger that that you over smooth things, and in the end, you don't your data is not really 100% representative of what you measured anymore. And you really, really, really need to understand the algorithms that you use for your analysis. Okay, so I think most people have that. We just had a little bit of a computer glitch here as well. But this is how you load in individual patches. There was something else I wanted to say but forgot about. Um, yep, now let's load in a bigger one. So just to show you, we won't have time to actually do local proxigrams today, but just to show you the principle. And that's, you pick, for example, I'm picking the big one here now, and go patch to obj. Where's the last one? Just precipitate. I'll just write over that one. Who cares? Replace. Delete that one. File. Import wavefront. Test precipitate. And now we've got the larger one here. Larger ones. It's actually multiple precipitates that have grown together. And you can already see you've got a hole here where they actually have grown together. And apart from that, there's a little channel in between. And here in these precipitates, we might want to have here it's not as representative, but we might want to have a proximity histogram from this part, and if there wasn't the second precipitate, we might want to have a proximity histogram just here, which is essentially, or we might want to have one along the corner and one along the face of the precipitate. And to do that, we're going to use something called Vertex Groups. So if you don't have any isosurfaces in Blender right now, what you can do is just load in the default monkey. Just open Blender and load in the default monkey. And then there is a tab here, which is the Mesh tab. And that's what we're going to use a lot in the near future. And here, most of all, we're going to use vertex colors, which is later when we're loading in analysis results, because they're usually colored surfaces. And what we're going to be using now is vertex groups, which means if we go into edit mode, so hit the tab key, go into edit mode, we can tell it that certain parts of the mesh are special in one way or another. So you can go, for example, and mark this area. Oops, that was a bit too much. So in this case, you could just... So what I like to do in this case is actually just get rid of everything I don't need. So you can just go and zoom out, press Z, so it will become transparent, and just mark that bit and press H to hide it. And now you see it's all hidden, and we can work with the remaining parts up here. We can zoom out and go and just mark this bit here. If we wanted to calculate a proximity histogram from down here, or interfacial axis or something, and then go create a new vertex group by pressing plus here and name that vertex group. So we might call it precipitate underscore bottom. You could use spaces, just avoid it, because I don't know, maybe in your... Oh, damn it, now I've deselected it. Just make sure that you're selecting everything you want to select, which might demand you looking into it in more than one perspective. Okay, and then go hit assign. And now, once those are assigned to the vertex group, you can try and press select, and it will select the same vertices again that you've selected now, that you had selected before. You can have as many vertex groups as you want, so we'll have another one precipitate underscore edge, where we might want to analyze what's happening along this edge here, and not with these vertices here, just along the edge here. So now we've marked the edge. Maybe we should deselect everything that we had selected before. You can use a little bit of trickery with that. Still one, come on. Oh yeah. There's a couple here we didn't select. Okay. Anyway, for proximity histogram, it wouldn't matter too much. But just make sure that you capture all the ones you really want. And now assign that. And now if we deselect, we can go select this part, the edge. Oop. And we can select the bottom. Okay? And this is something we can load into Matlab by exporting that surface. So, sorry, if we go Alt H for unhiding, this actually only applies for what we've been working with. So we can go select that bit, select that bit, deselect that bit, and it's still marked. If we're out of edit mode, we can go File, Export Wavefront. While forward C up, just make sure that that's true again. Selection only. No modifiers. We don't need the edges. No normals, no UVs, no materials. The faces are already triangles, so well, we could leave it on. There is no quartz anyway. And what we need additionally here is polygroups. So I also need to mark polygroups. And then probe tutorials, test precipitate, Vertex Groups. And now if we export that OBJ, and we open it up, then you'll see, well, we've got a lot of vertices. But once we get to the faces, you will see G null, which means the faces that are triangles that are coming afterwards do not belong to any vertex group. And then at some point you will see a G and a name. So for example, oh come on. We didn't mark too many, so it will probably take a little while until we get there. Hope I didn't scroll over them. Ah yeah. So for example, here we've got precipitate edge, and we know now that this face belongs to precipitate edge, and so on and so forth. Precipitate bottom edge, and so on and so forth. So there's one subtlety that you need to know, or a couple of subtleties. The first one is with vertex group exporting in wavefront OBJs, each face can only belong to one vertex group. So if you accidentally, like me before, you can see this row of vertices also belongs to both the precipitate bottom and the precipitate edge. And then Blender tries to figure out as a best guess where to put it. But in the file, in wavefront OBJs, the vertex groups are actually by faces. So certain vertices can only belong to a certain group by belonging to a certain face. Whereas here we've marked vertices directly. So what that means is that if you select vertices here, then it would also include this. So if I selected these vertices and I export them, it includes all of the faces that touch vertices that belong to that vertex group. So in other words, it will for this vertex, it will also take those three triangles because they belong to that vertex, which means it also takes these vertices. So it essentially moves one row of vertices further. That's something you need to bear in mind when you do that exporting. That's just a discrepancy between us marking vertex groups by vertex and Wavefront Obj is actually having polygon groups rather than vertex groups. And each polygon that belongs to a vertex that's part of a vertex group will be exported as that. And then of course we've got the best guess thing because it can only deal with one vertex belonging to one vertex group or one face belonging to one vertex group. So far so good. It shouldn't, it's not usually a problem because you don't want to analyze overlapping regions anyway. You want to analyze the edge versus the flat part of a precipitate, for example. If you're doing supralloys, it's a task we've been seeing a couple of times. And so far, you would put in analysis cylinders and play around with that, which is pretty annoying. It's just much nicer if you have an analysis file and you can mark certain areas and do analysis locally. And then you load it into Matlab, which is probably the last thing we're going to do for today because we're sort of running short on time. Using the Obj To Patch command. So this is the one that does the that loads in the OBJs and recognizes. Well, you can use it to load in any OBJ, but this one also recognizes vertex groups. So you'll get two outputs, and the first one is your OBJ, and the second one are the groups. Probe tutorials, test precipitate with vertex groups. So the first part, the OBJ, is like the OBJ that you know or that we always used to have. So you've got your vertices and your objects, and you can turn that into a Matlab patch and keep working with it. The second variable are the groups. So if you open the variable, you'll have two fields. It's a struct with two fields. The first one being the name of the group. So give them reasonable names so that you later will remember what's what. In a file with 50 precipitates, maybe precipitate bottom is not the greatest name, but anyway, can get creative with that another time. But anyway, give it just some reasonable names. And then the second part is the vertices, and that's just a list of all the vertices that belong to that vertex group that we've defined in Blender. And that's just for our proxigrams and for our analysis later. Proxigrams and interfacial access. Interfacial access maps, I haven't implemented vertex groups yet because I don't see a reason for it. Mainly because it analyzes local variations anyway. So why marking local regions? Maybe there will be a reason at some point because you want to have different parts analyzed in a different way because of the scaling of the results, stuff like that. It's possible. Sorry. But anyway, you get the groups out, and you get the vertices that belong to the groups out, and that's later what we're going to feed into the local proxigram. I'll just show you what the inputs look like, just for next time. Sorry, so this one is actually not the quick version, so it also has the error statistics and everything, and the counts if you want to do manual analysis with it later. But what you need to put in is the parent pos file, the interface as a patch again, then the species pos, so whatever pos you want to analyze, the bin width, and these four entries are the exact same as we always had for the proxigram, and the only thing that's extra is the vertices, where you specify which vertices you want the proxigram to be calculated for. Okay, I think that's it for today. We didn't get too deep into volumetrics. I think that's something again for next week. Um, I'll just maybe quickly show you how to do it if you wanna try it on your own. So what you need to do is you need to add a domain. Shift add. No, sorry. Shift snap cursor to center. Otherwise, it's gonna be offset somewhere. Shift add mesh cube, and then we will move that cube up GZ1 just so that the origin of the cube so that the origin of the cube is at the bottom. That cube will get a material, and that material is a volume material with an emission of 1. It's very important. We'll need the emission for later as well. And then we'll go into textures, materials textures. So if it's on world textures or drawing textures, that's not what we need. We need a materials texture. And there it's going to be voxel data. I got the voxel data. The voxel data is 8-bit raw. So with the new version of Blender that's coming out soon, there's also going to be OpenVDB integrated, which I'm personally very excited about. And so we will have more options to do volumetrics, faster volumetrics especially. So load in the raw file, still frame only, frame 1. That's important if you want to do animations later, because otherwise it's gonna mess up anyway. I'll explain you why it will mess up later. And on that one we've got 94 times 94 times 236. So we'll scale this cube to that size. Dimensions, what is 96? 96, right? 96 times 230. 96, sorry, times 96. Just zoom out, and there we've got the precipitate in there, and hopefully our volume data will look okay with the precipitate. No, it won't, because that's from last week, so it's still got the XY shift. Anyway, I'll finish it. I have the time to recalculate. So 48 times 48 times 119, so it's 48 times 48 times 119, and by now it should look okay here. Yep, that's all fine. And if we go into rendered view, we should see something. Yep. Last time I hadn't switched the emission on, so there was no light in the scene. That's why we didn't see anything. Haha. And now we need to define the influence, and the influence is multiply. So essentially that means it's multiplied with 1. And we want to influence the density. And the coordinates are the object coordinates of the cube. And there we go. You can't see much right now, so we'll just switch the other mesh off. And RGB to intensity. Oh, we don't need that. Well, we'll ramp the color. Look on the colors, ramp, and now we're ramping from ramping the colors rather than just multiplying them in straight. And now we've got all the nice voxel data we can handle. By the way, while you're doing that live, you can set the step size, which is the binning for the renderer, to a larger value. Then it renders a lot faster. So you can see if it was on 0.2, it takes quite a while. It actually has adaptive rendering, so it starts out coarse and goes finer and finer and finer, which is already a lot better than just rendering it straight out. But anyway, if you leave it on 2, you can see on a modern laptop with good OpenGL, it does it pretty much in real time. What we would do with the coloring is just change it to some ramping. So we'll add another color mark. Sorry, we'll add another color marker. Make that the 0 color marker, the first one. Sorry, blue. The 1 color marker we'll make green. And the 2 color marker will make red. So now we're looking at the outside of the data set, and most of all at these voxels that are sort of have too high values. That's why it doesn't look quite right. The other thing, oh, sorry. So if we go, so the other thing we want to do is probably do a cut through it, because otherwise you're not going to see much. We're just looking at the surface. And to do the cut, we'll just add a Boolean modifier, which just takes a slice out of it. You'll see in a second what that does. So we'll just add another cube. You can clip it by any shape you want, by the way. So S20, S shift Z5, and then maybe just put it somewhere around here, and then go with the other cube and go into the modifier Boolean intersect. That's fine, and we want the other cube, and now that cube is scaled by that cube. We just hide that one so that it's not going to block our view. And now if we go into rendered view, it's still got map to bounds set. So sorry, my bad. So you need to go back into the textures, and then it switches to brush textures for some weird reason anyway. And here we've got map to bounds, and now it's always trying to map to the new bounds of the object. And if we don't do that anymore, we've obviously clipped, oh sorry, 0.5, because we've offset the anyway, I'll tell you next time why you need to type in minus 0.5. But now we've got a nice cross section. The only thing we need to do is probably crank up the intensity a little bit. And yep, there's our precipitates. And yeah, we probably need to write an algorithm that gets rid of all those weird sort of noise things on the outside. But yeah, I think it looks quite nice, and you can do a visualization together with everything else as well. It's a bit grainy here. That's what we did to it when we set the step size to 2. But for render purposes, we can set it to 0.1, and it looks all nice and clean. Okay, so more volumetrics and local analysis stuff next time. But I think at least now we've got reasonable algorithms that can help us to pull data in relatively quickly and not having to throw stuff around too much. Any questions? Game